Okay. Now consider the case. Okay. Case 3. Okay, when both J minus and J plus are neither entity in our final, and hence they must be infinite. So whereas the infinite number of terms are lying on this side and the infinite number of terms lying on this side, why you still can have convergence? What should be the argument? So if this is the case, consider two sequences. So xn subsequences. Xn where n belongs to j minus. So this is a collection of all those terms in this sequence xn which are on the left of a, and xn such that n belongs to j plus, so it's a sequence of all those terms which are on the right of a. Okay. Now these two are subsequences. These two are subsequences of xn where n is anything. Okay. Why these two subsequences are going to converge to A still?
Because parent sequences.
Exactly. So we have the invariance property. Yeah? Invariance property. Since this guy is converting to A, so both are going to converge to A. Okay. As xn n belongs to n converges to A, so does xn or n belongs to j minus, and xn belongs to j minus. Okay. Now what does this mean? The convergence of this to A. It means that for epsilon positive, there exists, say, N1 and N2, for example, such that the xn minus A is less than epsilon for all n bigger than or equal to N1, and xn minus A or less than epsilon for all n bigger than or equal to N2, and I should say that this n belongs to J minus and this n belongs to J plus. Okay. When this condition is going to be satisfied, maximum. Oh, okay. If this is true, this implies, forgot something. This implies that f of xn minus L is less than epsilon for all n bigger than or equal to N1, and N belongs to J minus actually, from this. And f of xn minus L is less than epsilon for all of n bigger than or equal to N2 when n lives in J plus actually. Okay? So when these both conditions are going to be satisfied simultaneously, just choose n to be maximum of N1 and N2. If this is the case, then you're going to have f of xn minus L less than epsilon for all n bigger than or equal to Ln. No,
Yes.
f plus n. That's what it will be. Okay. Agreed? Question who asked first? Sorry. This can be anywhere. So it doesn't matter whether it is in J plus or J minus. This condition is satisfied for all n, whether it is in J minus and J plus. So since this is true for all n, we got this label. So no matter what situation is, you have the components. Okay? So here are things for you to do. You need to do the algebra of limits for yourself. Okay? Do it in basic sense. And if you have a limit x approaches to A, x equal to L, and x approaches to A, g of x equal to M. Okay. Then x approaches to A, alpha f of x plus beta g of x alpha L plus beta M. Okay. That's what you have to do for yourself. I mean, because this is nothing. So this limit is the existence of this limit is nothing, it's just something in the terms of convergence of sequences, which we know very well actually. Okay, so it's just peanuts. We can use algebra of sequences. Therefore, second thing, prove that limit will be f of x, g of x, Lm. And third thing that you should prove is that limit x approaches to a f of x, g of x is L over m. Additionally, you need to assume that m must be non-zero and g of x should not be zero as well. It's to 30 minutes. Great? Now, I would like to get to. So there are loads of exercises, little exercises, and so on. Do every single them of. So you can also think about doing exercises from the obviously more challenging than more fun actually. Now I would like to come to the equivalent definition of limit. Might have seen that. To call epsilon delta definition. That's correct. We're going to prove, we're going to explain what is epsilon delta definition. And then I'm going to prove that this definition of the existence of the limit is equivalent to that epsilon delta. Both are equivalent. Either one of them. Obviously, this is going to be very useful this definition in the terms of sequences is going to be very useful if you are in R actually. So in R, this is the best way to approach. But if you are in general metric spaces, you need order in metric actually. This can work if you have order in metric. The other definition that I'm going to write now works in all these. It's any kind of. Alright, so I would like to imagine I have two metric spaces, X and Y. I have a point here A. I have a point here L. Now, this is not necessary that this should be the whole space Y. So we can also talk about a subset of Y. Okay? And this L can be inside E, and it can be also outside E, but it must be a limit point of E. Generic sense, L is a limit point of L is a limit point of so it could be inside, it could be outside. And as for the function, this is what the domain of function is. Okay. After the function that takes values from this domain, okay. and even in this domain, this A could be inside basically D, and it could be outside D as well. But we need to assume that A is a limit point of D. So after the map which throws the point of D into E. Okay. So what I would like to define is that if I am getting closer and closer, so it's like X is arbitrary point. So in this domain D, I am getting closer and closer to this A, then my f of x for this x will be, this is the image, this is getting closer and closer to R. That's what I like to define. How can I define it? How can I define this real list? Basically, that's what we want. That's what we want. That's what we expect to have actually. Okay. So we want f of x to get closer to L actually. So how we basically say that something, a point like a set of points gets closer to L. What you say in the terms of distances. But if it is really getting closer to L, then what should happen? Huh? You take any neighborhood of this. Okay? You take a neighborhood of L. Okay? Centered at L of radius epsilon. What can happen? We can always find a neighborhood of X with a neighborhood delta of A, obviously, oh sorry, of A with the radius delta, such that if X is falling in this, neighborhood of A, then all images of X, f of X, are going to fall into this. So in other words, what we are saying that I want f of x and L to be closer. How much closer? Closer than epsilon. Okay. Then if they can be really get closer, then you should be able to find a set of inputs. Okay. Such that if x gets closer to a, then f of x will get closer to what? So in other words, for every of our wish, which is epsilon, we can always find a delta. Okay. Depending on epsilon. So obviously this should be part of D actually.
intersection.
No. This should be part of D. Could be because if A is outside, okay, then you can have intersection. But it should be part of D because you are operating F1. So if you are taking something outside domain, the function doesn't make sense.
And sir, D को हमने open set लिया हुआ है.
I don't have any condition on this. Okay.
T नहीं लेती.
Okay, I can assume for some practical reason I need to assume things to be open. Okay. I mean, if you see Rudin book, he's not talking about D. He's taking the whole space X, which is open by default. Okay. Which is open by default. Fine. Not getting into this sophistication, but I'm saying that okay, if this is a domain and I want f of x to be closer than epsilon, then my x's should be closer to a than by this distance basically. So if I can play this game of epsilon delta, so for every epsilon I can always find delta, we're gonna say that okay, this guy is really getting good. What should be the definition? We will say that for every epsilon positive, we can always find a delta positive such that if the distance between x and a is less than delta, this is going to imply that the distance between f of x and L is smaller than epsilon. Okay? Well, obviously this distance is going to be in space x, well, this distance is going to be in space y. For the practical purposes, assume that the domain is whole x actually. This definition. Like agree with the convention of Rudin. I won't put too much stress on x. So imagine that the domain is whole x, but the outputs are sitting in E. Where L is the limit point of it, so it could be inside and outside.
Then A should be point of.
So if we take x, y to be r, and this distance to be, what you call Euclidean metric, okay, then we can translate this into what the classical definition, that x minus a, for every epsilon positive we can, x minus a less than epsilon implies less than n. Delta implies so essentially we are saying that if you choose a neighborhood of L, then you can find a neighborhood of A in such a way that all axes from this neighborhood are going to fall into basically this neighborhood. That's what this is. Can have multiple positions. So what I would like to prove that these both definitions are equivalent. The next thing that I would like to prove that these both definitions are equivalent. Otherwise, that's two ways to say the same thing that you So, but what I would like to prove that limit x approaches to a f of x equal to L. Okay? We know this is true if and only if for all xn is not equal to a, such that xn converges to a implies f of xn converges to L. Okay? You know, this definition can exist in metric spaces, but not the left hand and right hand limit. Now this can exist. This can exist. And if and only if,
The other one.
so we know that this means this actually. So far we have defined it. So I would like to prove that this is equivalent if and only if. For all epsilon positive, I can take out a delta such that whenever distance between x and a is smaller than delta, this is going to imply the distance between x and L is smaller than epsilon. Agree? Which side is obvious?
Same.
Okay, consider this side. Why this side is obvious? Imagine this is true. Okay, and I would like to prove this. So if I would like to prove this, what does this mean? So I need to pick a sequence such that xn converges to a in x, which should imply that this converges to y. So let xn be a sequence such that xn is different from a and xn converges to a, okay, and then goes to okay, illustrate that. Agree? What does this mean basically? What does this convergence mean in metric space? Have you done definition of convergence in metric space? Okay. So this means for all epsilon positive, there exists capital N such that between xn and a in x is less than epsilon for all n bigger than or equal to n. Why we are done almost? Because we have hypothesis. What is hypothesis telling you? That whenever this happens, this will happen. So now since this is happening, what does this imply? That the distance between f of xn and L is less than epsilon for all n bigger than or equal to n. Why? Okay, if the delta is epsilon, choose epsilon to be epsilon. Same words. It doesn't matter. Agree? So if this is true, what does this mean? That's what the definition of convergence in Y is. This implies that f of xn converges to L in Y as n is to infinity. So we are in the one side. Agree? Okay. Let's carefully think about the other side.
Okay.
Let's try to do this side. Okay. So when we are assuming this, we have two things in our hand. So we have that for every xn goes to A, we should have f of xn convert this to R. Okay. Then what we like to prove, we have to pick an epsilon positive. Then we have to find the delta until then this happens. Do you think that how should we do it? Suppose not. What will happen? Suppose this doesn't happen. What's going to happen? What would be the negation of this state? Do I need to tell you that? What is the negation of this state? So there exists epsilon positive such that for all delta positive,
Negation of this.
there exists x in E, x in E. There exists x in x actually. Yeah?
Yes.
There exists x in E depending on delta. Depending
So it's Y.
okay. We're not taking E as subset of Y indefinitely, it's taking E to be subset of X and form. It's like the first picture over there. Okay. Let's read with this. So there will be X actually in X E. We treat E to be subset of X. By definition of Rudin. Then what's going to happen? Pxa less than delta
But
and
this if of x
distance between
if of x
Will be right.
f of x and
greater
L is bigger than or equal to epsilon. That's what is going to happen. Why this is a troublemaking thing?
Because for all epsilon positive, Bx, B of x, A is less than epsilon. Means xn converges to A.
Choose
Let's see.
what might happen.
Can you see f of u? F of x.
Choose delta n
It's
in one more n. Okay. And accent from so it's like, what does this mean? This means that x belongs to, I mean, in the terms of, for
A
example,
minus-
R, we say A minus delta n plus E. Then I can, from each ball, I can choose, so let us choose xn from the ball with the radius 1 over n and centered at P. For every n, like for every n, agree? If this is the case,